Então, boa tarde a todos, sejam bem-vindos. Antes de começar essa palestra, eu gostaria de falar rapidamente sobre o 3E, porque essa palestra é possível graças ao suporte do 3E. Então, o 3E é o Institute of Electrical and Electronic Engineers, que é uma sociedade técnica e profissional internacional dedicada ao avanço da teoria e prática da engenharia nos campos da eletricidade, eletrônica e computação. Então, ela promove o compartilhamento do conhecimento aplicado no que se refere à ciência e tecnologias da eletricidade e da informação. E o ramo estudantil do 3E são unidades organizacionais do 3E, espalhadas pelas mais diversas universidades do mundo, e eles realizam vários eventos locais focados principalmente em ciência e tecnologia. Então, se algum de vocês estiver interessado em fazer parte do ramo estudantil do 3E, e contato com os seus professores de engenharia elétrica, ou buscando nas redes sociais, o ramo estudantil de 3E, ou diretamente pelo site. Agora eu vou passar a palavra para a professora Michele de introdução.
Obrigada, Flávio. Bom, se alguém tiver interesse em conhecer o ramo estudantil do 3E, pode entrar em contato com o Flávio, comigo, o professor Marcelo Tavanello, da Engenharia Elétrica. Então, sem tomar mais tempo de vocês, vou dar início à apresentação da Francesca, então gostaria de falar algumas poucas palavras a respeito, porque a experiência da Francesca é enorme, então para não gastar muito tempo dela, é melhor vocês ouvirem ela falando, né? A Francesca tem mais de 20 anos de experiência em pesquisa e desenvolvimento na indústria e academia de semicondutores. Ela começou nessa área no mestrado em física na Itália, em 1996, e ela fez o doutorado na KUL, que é na Bélgica, em 2004. Atualmente, ela é professora de nanoeletrônica na Faculdade de Engenharia da Universidade de Tecnologia de Sydney e pesquisadora-chefe do Centro de Excelência em Sistemas Metódicos Transformadores. Essa palestra, como eu disse o Flávio, tem o suporte da IDS de 3E. A Francesca fala muito bem português, mas tecnicamente a gente trata mais em inglês. Então, se ao final da palestra alguém não se sentir à vontade de fazer a pergunta em inglês, pode fazer em português, né, Francesca? Aí ela responde em inglês, mas dá para você se conversar, tá? Francesca, muito obrigada por ter aceitado o convite de vir falar com os nossos alunos. Então, o palco é seu.
Obrigada, Fábio, pelo convite. E eu vou falar algumas palavras em português, depois eu vou falar em inglês mesmo. Mas obrigada por terem vindo aqui. E como a Michele disse, se vocês quiserem perguntar em português, eu vou pedir para a Michele fazer uma tradução e vamos conversar depois. This afternoon, I would like to share with you a little bit of our work in Graphene over the last 10 years plus. And as Michelle already said, I'm based now at here at the University of Technology, Sydney, which is, well, Sydney, I don't know if any of you have been there yet. Hopefully see some of you at some stage down under. So you probably will recognize this, the Opera House in Sydney, very famous. And our campus is quite central, so it's very, very close to here in walking distance. And so it's a very urban campus. This is our Faculty of Engineering. We are not the biggest university in Australia by any stretch of imagination, but we're still relatively big, so 40,000 students or less, of which a lot of them are actually international students, both at undergraduate and postgraduate stage. So, actually, Flavio already did a very good introduction to everybody. I still want to spend a couple of words. I'm also a member of the Board of Governors of IEEE, so I'm actively working in the society as a volunteer. And I definitely recommend, I always recommend my homework. So all of the students that are here, that are not members yet, I think it's a very, very good investment for your professional networking and future. So IEEE is really very, very good. Networking is everything, especially when you finish school, you want to move on to work, and you have the opportunity to link in with a lot of very established professionals all over the world, on top of having access to a lot of specialistic information, conferences at reduced prices, and of course, the distinguished lecture program, which is also very helpful. So definitely recommend any of you who is not yet member. Now, coming back to the more technical part of the presentation, before starting, of course, because this is actually, I will have concluded an hour, I promise, but I will have to go quite quickly on quite a few of the topics I'm going to talk about, and because there's a lot of work that has been done by my group and our collaborator during those many years. So I do need to at least show their names and mention all of them, but really are in Australia, but a lot of others are actually all around the world, Europe and in the US. And of course, my group, current members of my group, it's not a huge group that I have during COVID. And the sources of funding. There have been quite a lot of this in Australia. This has been quite important for me. I actually come from industry, so until 10 years plus, I was still in R&D on the industrial side. And the RCD, the opportunity to actually convert my career into more an academic career. Since then, being in academia, still working a lot with industry, of course. And yes, Australia DRC, FSRs in the US, and the laboratories in the US have been collaborating very closely with us, as well as the Australian defense. So I'll say a few words about that in the end. Okay. So this is more or less the outline. So I need to do a little bit of an introduction about this platform that we have developed over the last decade. And what is the relevance? Why we spend so much time on that? What are we trying to achieve? And then I will touch on some of the application areas. I don't think I will have the time to go into all of the details about all of them. So we'll potentially spend some more time on perhaps the optics and the biosensing. And if there is interest, of course, I'm very happy to talk to you after the presentation. Okay, so our approach to graphene has been quite different from the mainstream approach to graphene in the sense that from the start, from the inception of this program, we were very applied. Graphene, of course, as you all know, has been always heralded to be a game-changing material with a lot of very interesting properties that are not available in normal thin films, are only available in graphene. But the challenge has always been how to actually harness those properties, how to be actually able to transform those properties into something that can be integrated in a device, gets to work with those ideal properties. And you see that's really the challenge for graphene as much as it is a challenge for most of the 2D materials. So we were particularly interested in having graphene grown directly on silicon substrates. Not messing up, walking up with transfer properties and that's transfer approaches. I come from industry, as I said, and I think I can be quite positive in the sense that any transfer process is going to be exactly very, very extremely difficult to translate into an actual production process. So that's why we want to get away from that. And this is basically where we're going. There's a lot of very interesting properties that graphene is multifunctional. And there's a lot of different properties that you might be able to exploit silicon integration, for example, like in this 3D type of architecture, where you have each tile that is doing a different thing. And actually, I will show you a few of these functions. I will talk to you a little bit about local power sources in silicon. I'll talk to you in the end about biosensors and a little bit about photonic and optical systems that can be integrated thanks to this graphene study. All right, so graphene, of course, is not a new material. And it's actually, in my view, it's really starting to get into the time where people would like to see an application and material at a high-end application, not just a composite or things like that have been really done. But really to have like an electronic device containing graphene. Graphene is an active material. Now, and so it's all, but it's not all. And the thing is also that every every year we're learning something new about graphene. So you might have heard lately about this interesting clistronics, which is something that happens when you have two layers and graphene start changing the angle and finding the magic angle where very peculiar electronic properties can be achieved. And then, yeah, I always like to show this just for people to be reminded of the fact that because so coming from electronics, you certainly will be conscious of the fact that interfaces are some of the most challenging parts in the electronic device. Interfaces usually the developers had the interface works, right? And just imagine integrating a material like graphene where the whole material is interface. So you can understand how challenging this becomes. And you really have to understand interfaces very well and what type of effects you're seeing and what is happening to the system. So this is a part that is not completely yet well known. There's still a lot work to be done. Last but not least, graphene can mean different things to different people. And particularly for people like me who work at the fence in between electronic devices and materials for electronics, there's electronic engineers, but there's also physicists, there's also chemists, and each of us has a different understanding of graphene. If you talk to a physicist, graphene would be an ideal single layer graphene is suspended in vacuum like a membrane in a very ideal situation which has ideal properties. But in reality, as an engineer, you will know that once you integrate a thin film, this will be the situation will be completely different. And so there's a lot more things to be understood. And also, if you talk to a chemist will probably potentially consider other things like nanoplatelets and different aggregation of people. So we really need to understand the challenge exactly about when we talk about what we're talking about. And now this is also something I like to, this has come out on Nature a few years ago, but I think it's really important for us to understand and remember. It is often misleading to talk about superlative properties of freestanding the idea of graphene for benefiting applications, because most of the applications won't be based on just freestanding graphene in vacuum. Will have to be a different type of. Because almost always, yeah, graphene is combined with other materials, and I'll show you what that means in slides. Okay, so first problem that we wanted to tackle was how to potentially cover 300 millimeter wafers with graphene as a way to grow graphene in a very controlled way. And clearly, the initial approach of the flakes, which has been extensively looked into, wouldn't be exactly the best way to go. The reason is that even if you, let's suppose you would be able to grow a very large flake of graphene, as large as your wafer, and transfer the whole flake of the wafer, which has been actually done and demonstrated by IBM, but knowing that this would go anywhere. The reason is that once you have your graphene layer covering your wafer, all of the subsequent processes that you would have to go through, like with thermal loading, with mechanical, with perhaps even polish, chemical mechanical polish and such, would probably make that your structure at some stage will just stop up without needing and such. Because remember, to the material is just doesn't have any bonding in principle to the other, to the Z direction only. So what we want to do is have a different take and look into, so we focus on imitation graphene. You might be familiar with that because imitation graphene onto single carbon wafers has been actually extensively studied over the last decade plus. And this is some of the early examples of silicon carbon wafers, and you can see that because they're transparent, with graphene covering the whole area. And the way it works very quickly is that we actually use the solid source of carbon from silicon carbide. We extract the carbon from the very top of the silicon carbide. So carbide functions as a source, solid source for the graphene, but also as a template, because carbon example of carbide really has an example pattern on the top that will be mimicked by the graphene. And what happens is that when we bring this influx of carbon at very high temperatures, so typically above 1500 degrees into high vacuum, the silicon species will tend to preferentially leave the surface and leave an excess of carbon on top of the ingot. And that excessive carbon will basically reorganize itself as graphene polymetallic. This is how it works on silicon carbon wafers. But we said that we were interested in doing this on silicon. And there's quite a lot of reasons for it. So as you know, most of the infrastructure nowadays of semiconductor is based on silicon. It would be really good to be able to combine silicon technologies with graphene technologies. So we were really interested about, can we do the same by using the silicon substrates instead? And the obvious initial idea would be to silicon carbide can be grown actually onto silicon. So if we have that, why do we try and do the same? So bring everything to high temperature and play with the same system. So you sublimate the silicon species, and then hopefully you will get an extraction of feed just on top of the silicon carbide. Well, the idea is good, but there's a lot of challenges, and that's the reason why it has never really worked. Challenge number one, if you do a cross-section of the system, silicon carbide with silicon, you would already see that the silicon carbide, which is this one, these are different surfaces of silicon where we grow silicon carbide, has an enormous amount of effects. Because there is a huge mismatch, lattice mismatch between, so 20% mismatch between the carbon and the silicon, which is really hard to work. And so we can't get rid of these effects. And as you know, if you use this an effective template to grow something actually, you will get effects. There's nothing you can do about that. And this has been mostly always the case. As you can see here, for those of you that are familiar with spectroscopy, Raman spectroscopy of graphene, which is the quickest way to have an idea of what type of graphene we have, is it quality or not. Well, you actually focus on this part of the spectrum, so G and G are typical fingerprints of graphene. And in principle, if the layer was completely defect-free, you wouldn't have this effect. And the fact that you have an effect band, and not only, but the fact that this effect band is really high, even higher than the G band, it means that your layer is highly effective, potentially not even tuned. And this is usually what happens, unfortunately, if we try to translate this process to the silicon carbon silicon. The other problem is also that we can't, unfortunately, we're working with silicon, and we can't even go too close to the melting temperature of silicon. This on the silicon carbon ingots, this process in high vacuum really works best above 1500. So that's an additional problem. So yes, this doesn't work. However, there's a lot of reasons why it would be really interesting to have this kind of carbon combination. And some I have actually listed here. So really the combination of wide bandgap material with a conductive material like graphene. For the photonics, there is a very good capability of making magnet materials, and I'll show you later. Combining a high stiffness material like silicon carbide and graphene is also very beneficial. So there's a lot of highly biocompatible. I'll talk about that later. So anyway, there's a lot of drives, but we still need to solve how to go about that technically. And that's where we started working, as I said, about 10 years ago now. And we came with a different approach. Instead of just using that sublimation, thermal deposition at high temperature, we had to come up with a way to relax those constraints by the defectivity of the layer. And then what we decided to do was to use catalysts. Catalysts usually always help. They help to reduce the temperature. They help to make processes fast. And particularly, what we came up with was to use an alloy of two different catalysts. In this case, we chose it to be copper and nickel. And this was key actually to the process, because what happens is that the nickel, when you heat out the structure, will tend to combine with silicon carbon and silicon material, silicon carbon for the silicides. The copper doesn't really form stable silicides, but what it does, it is a very good agent for the hybridization of carbon. So these two materials, this alloy of metals working together, turned out to be really beneficial, because what happens is that, and you can see that here, remember the D band, you want to have it as low as possible. And for example, if you used only nickel, you can see here that we would have an ideal regime that's still pretty high, so not really very good quality and large grain size. But if you mix actually the nickel and the copper, you can actually reduce that ratio, not completely, we want to do miracles because you see the type of thing we're working with, but reduce it down to 0.2. This is a spectrum that actually relates this point here. And what that means is that we don't have large grain sizes. We have about 100 nanometers grain sizes, but it's a continuous and uniform layer of over single capacity, which is what we want to do. And I'll come back to the grain sizes. You will find out that in quite a few instances, this is a good thing to have. Surprising. So basically, if you want to think about our process in a different way, we are kind of in a hybrid in between the thermal decomposition where we use the carbon and silicon carbide, but we don't quite go at the same high temperatures, and the metal-mediated growth where people do CVD growth on, for example, copper or nickel foils, and then they have to transfer in flakes. And I also have to mention, as I said, if you treat the nickel only, you can potentially get hybridization, but it wouldn't be quite the same type of quality. And most probably, usually it also would, the system of graphene would catalyze at the top. So you would have to actually detach the graphene again and transfer it, which is not what we want to do. Which is not actually what we do here, because what we do here is that, very importantly, I forgot to say, is that this growth happens in a liquid phase. So we usually grow at 1100 degrees, and 1100 degrees and upper is liquid. Silicides are liquid as well. And so what happens is that as this process grows, so the amount of nickel will be linked to the amount of carbon it increase. And all of those byproducts will be floating. So it means that you will be able to actually do a wet etch and eliminate all of that, and just be left with things in carbon saving. And not only that, but you will be able to do that selectively, which I will show you in a bit. Before I get there, I also have to mention a couple of other things. Is that we did some synchrotron investigation of our layers, reasons that we can actually basically change the energies of the photons that we're working with. And by that, we can change, we basically will have very, very fun. And we can see, for example, if we only look at the top 2 nanometers, we have the actual graphene here, related to that, then silicon carbon underneath. And then, of course, when you start moving down, then you have the silicon carbon that comes up more and more strongly. But the important thing is also that we have quite a lot of oxidation just underneath, just at the top. So underneath the graphene at the top. Now, I would like you to remember that because it will come back for when we convert transport properties. Remember that interfaces. Okay, so this is really I would say, the most appealing part of this methodology is that we're able to be site selective. What makes that means is that because we're using a silicon carbide film on silicon, can pre-pattern the silicon carbide silicon in any way, any pattern we want to achieve, including green, pillars and such. Then deposit that metal alloy as a lacquate. It's a lacquate layer with no other additional lithography steps. And then the whole system will be recognized only where you have the carbon source. So only where you have the initial silicon carbon that was present. So this is really very good because you can imagine that instead of being having to transfer plate by plate or having to pattern it once you're building plate, you basically can not only do this already at wafer level, but this will also formally cover and coat all of the silicon carbide structures. And this was one of our first examples where we did this, and this was, again, a small wafer just as a demonstration. And it's where like the silicon carbide bridges that were suspended on top of silicon. And by looking at the Raman, you can see that wherever you see this black silicon, there is no graphene. You see that here, silicon. And the whitish part here, it is actually graphene with silicon carbide. Silicon carbide peaks are here, and this is the graphene. So it really works selectively at the wafer level, which is really something we want to have. But not only, this can be also scaled down with very, very small structures. And this was just a case vehicle to prove that. These are actually grown silicon carbide wires grown on top of silicon wafers that were done by some collaborators in Italy. And we wanted to see whether this process, like putting down these blanket layers of copper nickel, would also catalyze the growth of graphene around this very small nanowire. So the diameter is about 50 nanometer average. It turns out that that's the case. You see, initially there is no graphene, and then we obtain the actual wires coated by graphene. And there are some very interesting things that actually we discovered by looking into these nanowires. But the thing is that you don't need to coat everything around, because we work with liquid phase. And in the liquid phase, everything will start flowing in really high temperature. So all of the catalysts will flow around and cover all of the walls basically of the silicon carbide. And this is shown within. Last but not least, actually it's not even last, but to talk about transport. I talked about a little bit about the chain where I said you could eventually do a very, very large graphene and transfer it to a 300 millimeter wafer. We do that. However, it's probably good that I need. Why is that? Because actually, the van der Waals forces, which are the only forces that hold together the graphene to the substrate, are corresponding more or less to this type of joules per meter squared, which is in between 1 and 2 joules per meter squared. Now, this might not say much to most of you, but when I was working with integration, this would be the low end of the application of, for example, low cores of the electrics, where no CFP would ever work, because everything would break down and everything would just collapse and be very ugly and destroy the yield of the system. So basically, no one really wants to work with the side of energy integration. Now, it turns out that we measured the adhesion energy of our system, and we came up, this is the number actually obtained, which is about 3 times higher, so 6 joules per meter squared. Now, this is interesting because clearly this is not just van der Waals forces, right? They come, and this is just an example. Now we use the CP adhesion testing with our standard collaborators, and that's the number we came up with. So yeah, it's not just adhesion, not just van der Waals forces, but basically what's happening. Remember that I mentioned that we had about 100 nanometer ring size. And basically what happens is that the grain size is the effective side. And so at that effective side, you can have potentially volume to the line substrate. So basically it's all about the sweet spot. You would never be able to get that type of adhesion if you had just flavor, which of course would be fantastic if you wanted to have high mobility layers. But if you want to have something integratable, at the other end, you also have to give in to some other final sweet spot, basically. And I will show you that, of course, mobility is a different story, but in terms of productivity, which is the other very big drive for graphene integrated into semiconductor processes, this won't make a difference, actually basically making a difference. Okay, so these are, as I said, as I mentioned before, these are the different type of application that we're looking into. Some are more advanced, some are less advanced. Those advanced are probably gateway, devices of sensing, device sensing, energy storage, which is a slightly different tweak of what we talked about. Photonics better services, we were working on that. And the terahertz application is probably the youngest part. That's a very interesting part of learning more and more because in the terahertz application, high frequency application, we understood that it's absolutely critical to have perfect contact with graphene and the metal side. So now let's start with a few words about, I just mentioned, productivity. Usually in any of these applications, something that we're really strong. We want to achieve the best productivity possible. And it turns out that even though we have relatively small grain sizes, we have a pretty competitive productivity, actually pretty much comparable to what you would obtain with a micro-sized flakes onto the hexagonal, so the actual silicon carbide wafers, which is something really interesting to understand. So supported graphene, as I said, so graphene is never used as memory in vacuum. Usually would show a power relation between the mobility of the layer and the sheet carrying density of the graphene. So they don't change independently, of course. It changes the power relation. So you log representation, and that's where you should get more or less a straight. And this has been shown already in the actual graphene of silicon carbide the wafers of silicon carbide. And these are the triangles. These were silício points that we took as a benchmark. So you can see that all of the points sit on more or less a straight line, and all the points, of course, have the equivalent shear resistance. That's basically what happens. Now, if we do the same type of evaluation to our graphene that is having waves, I explained, and it has this 100. So another preamble important, this is my flake size, so grain size. Now, it turns out that our graphene with much smaller grain size also sits pretty much on the same trend. And indeed, I showed that the type of shear resistance that we get out of our layers is pretty much comparable to the one that you would get to silicon carbide wafers. And this is very important. So what really happens here, if you look here, is that all of our points, and these are the one-on-ones, the surface on one that we use, and these are 100, they differ by the fact that they find themselves all at the high end of sheet carrier density. And that's very important to know because, of course, when you are on this high sheet carrier density, you will never be able to get very high mobility scale. On the other hand, if you can reduce the sheet carrier density, you can climb up and achieve quite a good number of mobility. But we are all the same. So these are all equivalent sheet resistances. So basically, this is very important to understand. And actually, this is where we get to the fact that the interface is dominating our transfer properties, not really the grain size. The grain size, like at least not this regime. Now, the other part that I forgot to mention is that while this point set always an N-type doping, we have consistently a P-type doping in our layers. Why is that happening? Actually, here our communication frames have been very much of help because we described our system, the considerations we have, and this is what they came up with. So they calculated the Fermi level and the energies. And basically what happens is that in our system, I showed you before, the very top of the silicon carbide is oxidized. And this is very important because graphene, most of the doping in graphene is always by charge transfer. It's not because you actually have dopants in the graphene, but it's because graphene is surrounded by certain type of materials. And that was the case also for the actual graphene on silicon carbide, it was actually given that type of doping. In this case, because we have an oxidation, so oxygen appearing just in front of the graphene, this would induce a p-type doping. And most importantly, you can see also this is a 100, and this is a 111, so they have slightly different configurations here. You can see because it's to be that's how it happens. We do have also an alpha layer, like the case of the graphene single carbon wafers, which is a carbon layer which is not acting as graphene because it has every 3 bonds. There is a bonding reaction to where it's bonded to the single carbon underneath. But what effectively this does is that it shields slightly the charge transfer for the oxidation of one photon single carbon. And it's exactly what we see. So 100 with no shielding have the highest amount of charge transfer because so really extreme should get a density down here, while the 111s are at least partially shielded by the presence of this buffer. So that's exactly what is happening, and it's beta. So this is the difference with the conventional sublimation on single wafers. Right. Now that I said that, let's move into the applications. And I would probably have to see how much time I can spend each of them, but probably will have to be rapid, but I'll try to give you at least some ideas. So starting with the optical side of this work is done in collaboration with all of these different investigators. So we have been awarded the Centre of Excellence of Australia. There are 15 investigators across Australia, all experts in different parts of optics and materials. And what we're trying to achieve is the miniaturization of optical components, which has never been achieved as much to the same extent as electrical components, as electronic devices. And particularly, we are going to do that by using meta services and meta-optics. It turns out that our system, this silicon carbon system, is particularly interesting in this application. And particularly, we're considering mid-infrared spectrum. Now, first of all, what is the motivation for mid-infrared? And there's quite a few. Mid-infrared starts being quite close also to terahertz, so terahertz and quite close together, and they have a lot of similarities. Now, from an MIR point of view, what you could do is you can actually have sensing, chemical sensing and standoff like distances, so without actually having to touch physically your sample. And the reason is that there's quite a lot of molecules that have your fingerprints in this mid-infrared region. And it turns out that quite a lot of actually of the greenhouse gases have a fingerprint in this area, like methane, like CO2, and such. And so potentially, if you're able to sense in that area with very good, sensitivity and accuracy, you would be able to pick up also PPMs or even less amounts of these molecules. That is one reason. And the other reason, there's a lot of this bio potential too. Another one is machine learning. So you may know that LiDAR counterpart to radar using photons set different techniques is being developed for autonomous vehicles. Now, in order to have a good, it's based on time of flight. To actually do a detection, and you can start making a map of what surrounds you. Now, the thing is that in order to have an accurate map around you, you need to fire a lot of power in your laser in order to be sensitive enough. And if you do that using visible data, this is a hazard, really, because it's not safe. So there is a limit that you can't use, otherwise you will affect people's eyesight. And this is why a lot of the companies are moving to the infrared instead, because infrared is still a problem, but the limit, the threshold is much higher. So you require a lot more power and still stay really high safe. And in infrared, there's reasons to start looking in infrared. Not last but not least, in infrared, you have thermal imaging. And you might have seen some of the pictures that are really beautiful from the James Webb telescope. Of course, they're using completely different approach to using up to the right. That has to be cool, but okay, and the space is already cool for you. That's not a problem. But this is just to show you that they have been able to indeed probe the composition of the systems into different stars really far away because of the infrared that I just explained before. And also in terms of imaging, it's quite interesting. So they have a double NIR and MR system, and by comparing the images that you get from one and the other, they can also pick up different composition and different features of what you're looking at. Particularly, this was quite interesting. In NIR, we were able to distinguish that there are actually two different stars inside that this nebula here. So there's a lot of really interesting applications, potential applications for this area. And also very, very quickly, I won't spend too much time here, but what I wanted to mention is that it turns out that what we can use is, so silicon carbide, first of all, is a polar electric. And what happens is that in this red stratum band, which is the medium infrared, there is a red stratum band between the material and below, where the material behaves as a metal. And so it can, you can actually, it can support a surface foam. It's not a plasma, a surface foam. A little bit indicating less long surface foam. It's just a vibration of silicon and carbon at that specific band. And this is quite interesting because you can use it to, like you can use plasmonics, but in the medium red. But at the same time, we have graphene top. And what happens is that we can actually try and combine two. So yeah, this is only to show you that this is silicon carbide alone can be really high, well, low loss actually, low loss material. When you use plasmonics like silver and gold, you would have a lot of losses inside those materials. So you would have much quality factors and much more spread. But then what happens is that you only have a very narrow band, it's a strong band, and you can't really move it. That's it. Now, when you combine this with graphene, which is what we can do here, and just showed you, then what happens is that, so if you look at this dispersion curve, this is only the surface form response band of the, so this will be like a photon in free space. And this is the responsivity of only single carbide, just back at the angular flat situation. And when you combine that actually with the plasma that is supported by the graphene, what happens is that you can extend the responsivity, but not only, you can also tune it. So depending on the amount of charge concentration, if you're able to tune it, you can also move it up and down, depending on your charge. So this is extremely interesting. And we have started demonstrating in quite a few areas. So the nanowires that I showed you before, for example, we showed very quickly, I'll explain to you here. So if you had only nanowires silicon carbide, you would have volatility in this area, don't worry about that. But this will be the surface form response in the field, which is really the restaurant band. Once you've coated the wiring graphene, you start having actually split double response, and you extend it beyond the restaurant band. And then you can start actually tuning it with applying, for example, a gauge and such, which is extremely interesting. You can play the same games with nanoparticles. And the very interesting part is that if you wanted to use these nanoparticles, for example, for biological environment sort of applications, this will be really, really useful because, for example, they can absorb a lot of heat. And you're responding to infrared, which is not the for example, gold particles wouldn't respond very well. We would have to have really large particles to respond in that spectrum. And microparticles are much more difficult to be metabolized by the body. So that can be a problem, whereas these ones can be actually metabolized. And then we're looking into different ways of filters that we can design top down by using silicon carbide and graphene that we can then dynamically change. So these are the areas that we're looking into at the moment. And of course, we can, as I said before, we can really do any type of geometry at a wafer scale in the way that I just explained in the beginning. So yeah, just to wrap up, these are the different areas that we're looking at. We're looking at imaging by doing different pixels with different size and ratings and different meta surfaces, all in infrared. And also we're looking at doing zero, so surface enhanced infrared absorption, chemical analysis to really detect very low ppms of chemicals and potentially species. Right, so this is about, I think we probably have to jump on this part here, otherwise it will take too much time. But another area that we're looking into, as I explained before, is actually how to have a local power source by using this graphene silicon carbon, so this is a completely different area. And also the way we make graphene is slightly different. In that case, we really want effects. We want a lot of effects in order to be able to store energy in the system. So we do that a little bit differently, and what we do is supercapacitors. So we're not doing batteries in the case here. We're aiming at having integrated supercapacitors, so integrated systems where the graphene on silicon carbon acts as the electrode. Okay, so in this case, we are really just using nickel and doing that several times so that we have a lot of topography, a lot of surface area, and also quite a lot of specific effects that allow us to store and use most of the carbon. But I won't have time to talk too much about this, so I will go forward to the next point, which is presentation. There's a lot here, so I close it. So, try and retrieve. for that. There's always technology. Right. So the last application I definitely wanted to talk to you about is really different, and I think this will actually open a lot of the next future electronics and beyond that. Also, a lot of the biomed application that is will be really interesting. So we started using this system of graphene and silicon as a biosensor, as I mentioned before, but a specific type of biosensor, which is a neural sensor. You probably have heard about this before. You might have heard about brain-computer interfaces. It's something that is not really coming of age, which is brain-computer interface is an interface that allows you to have a direct communication from your brain to another remote electronic platform or machine. This without having to use any brains. And there's a lot of applications for that, as I said, they go from biomed down to consumer. And particularly in this project that we talked to you about, we were very focused on defense defense application. So that's India. And also the other, so this was that was in collaboration still going on with my colleague Sydney from University of Technology Sydney, who is an expert in this area of PCIs, as well as algorithms and AI, which is really part of this work. So here is. Yes, and then of course there's quite a few other people that are involved, including people from the actual Australian Army that have tried the sensor on, and they have done some field demonstration and eventually here if we get to do that. Right. So, and then just a very brief introduction, because many of you may not be very familiar with this concept, but you might be familiar with electroencephalography. This is something that's been done already for a long time in the hospitals. And the idea is that the patient or the person can undergo, so is covered by a usually sort of swim cap sort of helmet, which is linked to brain sensors, which are quite simple. They are wet sensors usually in hospital and clinics. And it's used to do a lot of really basic diagnostics about the state of the brain and your mental states and such. And a lot of things actually can be inferred by this type of signal. You go to epilepsy, so you want to, before the scene actually, the actual seizure should be able to actually detect it. Sleep disorders, insomnia, narcolepsy, cognitive load stress, very important for young, as you can imagine. People that have been subject to brain injury because of, in Australia, we play a lot of rugby and that type of thing, and it's quite heavy on people. Neurodegenerative disorders, this is something that's happening more because the population is aging. And most people know that this type of degenerative diseases, if caught early, you can stop them, maybe not reverse them. But if caught too late, then it's going to be much harder to do so. So you would be like to have a way to actually detect this early and potentially not going to the hospital for that, spending like a whole night under observation, but just doing a point about your normal life. So there's a lot of really very interesting potential here. And more recently, this part is, which is the brain-machine interface or brain-computer interfaces, which is again just being able to send comments out of the brain directly to your electronic machine. How does that work? So a little bit of an introduction. So this works based on the collective oscillation of the neurons in the brain. So you won't see the single spikes, but you will see the collective oscillations that actually are in very slow frequencies. So usually they're below 200, 150 hertz, down to just a few hertz, like delta band. So each of those bands gives some different information about the state of your brain, for your position, and they relate to tens of thousands to up to a million neurons oscillating all together. So firing together. The oscillation comes from the neurons, and neurons you might have seen before, the how they're structured, and the submania. various synapses, then they have an axon that communicates down to the next synapses, down to the next neurons. Now, what happens is that when a neuron is given a certain input from different adjacent neurons, if the threshold is passed, then it will be a start of depolarization. So basically, the action potential will start, and will go down the axon and will be transmitted down to the next synapses. And this is the usual disappears for one single neuron. And then just imagine millions of neurons together give some selection. There's people using implanted devices to do that. And the advantage is that you won't be able to place the implanted device down into the cortex. And because of that, we have much better resolution as we can understand. However, of course, it's very invasive. And you have to do undergo surgery. There's quite stringent biocompatibility issues that you have to work around. So usually those type of applications are really limited to people that are severely disabled. You need, for example, pencil climate, the type of situation or interruption of neural pathways and things like that. Other than that, you like really to be external. And at that point in time, you're going to have much less spatial temporal resolution, but it's just where you put it on, whatever you want to. So it's a big barrier, it's basically form. So that's why we are based on machines. You want to stay away from surgery, basically. And now, how this works is quite complex, so I would be able to give all the detail, but of course, depending on what you want to look into, you will have to place your sensors. So this is the structure of the brain, different lobes, the cortexes, right? And if, for example, if you want to monitor cognitive stress load, you would rather put your sensors in the frontal and your forehead. But if you're monitoring other things, like for example, we are now using a steady state visual induced potential. So it's a visual stimuli that we bring in. Now, then we need sensors here corresponding to the occipital lobe, because that's where the visual cortex is placed. So depending on what you want to do, you really need to place your sensor in very different places. Let's do that again. Just to see which one was before. Okay. Okay, so now what we're going to fit in the story. We think the story that in order to take this capability out of the clinical setting, we want to get away from wet sensors. In the hospital, you will have noticed that people have to inject gel into sensors because the gel will make contact with skin and will maintain that contact. It will be a totally resistant contact for the gel, the conductive gel, and will be maintained for a while, but not for very long, because the gel will actually dry out. So when the gel dries out, of course, the contact with the skin will start degrading. And that's a problem, because I didn't mention that the biopotentials that we're looking into, you've seen the serum alpha, delta, and such. The typical amplitude is just a few microvolts. So it's really, really important that the contact impedance is as low as possible. So basically, these can't really be taken out of the clinical lab, and we need to go with dry sensors. So basically, novel dry sensors so far have matched the same contact properties as the actually wet sensors. That's an important thing. Any dry sensor has a much poorer contact impedance and also some other problems of biocompatibility and such. So there is actually a very high need for extremely good dry sensors, and that's where the graphene comes in. Now, it turns out that graphene is biocompatible. Graphene can be intercalated, as you remember, And there's some interesting stuff happening here. So what we decided to do is to look into potential of this system as a sensor. And what we're doing actually is very simple. We're just using it as clear of this graphene single carbon silicon, so it's very, very thin, and connecting that to the backside of silicon into the socket of the helmet through a pin button. Now, very tricky. If any of you are interested to know, to tell you, but we are able to make the system completely so liquid and it conducts so well. So basically, any signal that we can sense on the top from the graphene can be very well transferred through the back throughout the silicon. We use highly conductive silicon, and by making a nice backside contact, we can extract it without any other contribution. So it's really, really simple, very thin, and very easy to integrate into a helmet. Turns out that graphene is very conductive, as I said before. On top of that, it's very compatible, and also, if you can see here, for example, these are some of the phones and other commercial sensors that we were benchmarking with. And you can see that all of them actually show a much higher output impedance than the sensor that we're using, just very, very thin graphene single carbon silicon. But not only that, the first test is different from, for example, the third one. So we have an original preconditioning, we call it, and after a couple of tests, we actually get to see values that are much, much lower than the usual ones. And this was particularly interesting. And they are particularly extremely stable saline solution. You know, as you know, in sweat, there's a lot of sweat and salts present on the skin, and a lot of metals can corrode it, for example, or composites can be started with laminate. This does not happen in the system. Graphene is very resilient, and the adhesion is high enough to maintain very good reliability. And actually what is happening, which does not happen if you have large plates of graphene, is that you can make this graphene from hydrophobic, so completely hydrophobic, to quite hydrophilic over time, just by the fact of keeping that in contact with the moisture of your skin. And this is exactly what happens. Basically, our model is that we are functionalizing the pH groups and related the grain boundaries of our grains. And little by little, then we're starting to attract about thin boundary layer of water. So making it better, that's what we see here. We have gone from 70 degrees contact angle down to 30 or less. And if you use a large grain size graphene, you couldn't do that much. By the way, this corresponds to a really important drop in contact impedance, which is what we're after. And after that, it remains really stable, which is really of great help for what we're trying to do. And I just wanted to show you very quickly the difference that it makes. So I talked about contact impedance, but also just imagine, this is the 1020, sort of basically the map skull that people use in EEG. And we're using the frontal at the moment. We're using the frontal channels with graphene. And we're swapping that between our graphene sensors with the commercial sensors. And this is a signal. Now, don't worry about what that means, because that's a different story. But all that you really can see is that the level of detail that is picked up by the graphene sensors in this case is much more detailed, is much more accurate than, for example, these pretty things here. There are much more, yet much less detail, and certainly the full metrics. So here you can see that the contact impedance transfer really relates to the quality of the signal that you're going to pick up through the helmet. And this is key because, again, we have to identify very accurately certain events that are caused by this PCI paradigm. Now, I won't be able to get into the details of that, but I'll just show you very quickly what we have in applied this term. And actually, we're very proud to have graphene sensors going out into the field, the real field, together with the army, Australian army. So the actual soldier, insurgent in the Australian army. trying our system. So there is a HoloLens here. So basically a stimulus, a visual stimulus is given through the HoloLens. The soldier chooses is given different, actually if I could play that visual video, you will understand much better what I'm talking about. And this children has to Shelly, can I ask you to connect again? Because I think it's really much. See, just try once and it doesn't work. System to usually works. So to finish the system. Anyway, if you have any interest, there is a YouTube link and you can have a look. Basically, it's Damien, our collaborator here, explaining what he's doing. And while he's using our system and commanding remotely in hands-free this robotic platform, which is a orthopedic doctrine. And what happens is that it's given 6 options on its comments, and they all figure different frequencies. And when it chooses one of the options, they go ahead and move forward and go to that specific point. It needs to focus on that specific frequency, so that specific option. And that frequency will be picked up directly on the cortex by the sensors that are placed here on the occipital part of the skull. And so that the information will be sent to the decoder that will do the classification, decide, okay, this is the common, and be sent out to the robot. And it actually works. Unfortunately, I can't just show you here. But yeah, we actually were really, really happy during the last demonstration when we have managed to achieve 94% accuracy by using the sensors. So that's really like a very, very good result, being early result. The sensors are always indestructible. So there's no corrosion problem. There can be high temperature, like people, of course. They really work for the audio reliability, which is very important. And now what we're working on, of course, there's one catch that I need to talk about, is that usually people zero out, like me, that have lots of gain. And that's the problem that we're trying to solve. Because unfortunately, we can't ask everybody to shake their hair like we can ask the soldiers to do. So that would be one of the next challenges for us. And yes, so basically I come to the summary. Sorry for hiccups with this technology here. Basically, yeah, I convinced you that this platform is not an high-mobility platform. So if you're talking about that type of application, you should be using this. Nevertheless, there's quite a lot of what we call more and more capabilities that can add to silicon for different purposes, as sensing, for energy, for mid-optics and services, as I said before. And it can be really done at the way of scale and pretty much compatible with the actual semiconductor processing, which is actually something really important if you want to scale it up to get large scale applications. So thank you so much for your attention, and I just wanted, as a last thing, let's do some advertisement for NRS Spring next year in San Francisco. I'm working, actually, this is part of an initiative that I did with EDS, which is let's bring more together materials and devices, because as I showed before, to keep materials really good, make some big changes, but we really need to understand much better each other and what are the different strengths in order to get the final result, which is a highly performing integrated device. And that can only be done with co-development and really working together. So hopefully some of you will consider going there, contributing to this initiative. So that's it. Thanks for your attention. I'll be happy to answer any questions.
Any question, any comment that you'd like to do?
Thank you, Francesca. Very interesting talk. I just want to ask about this EEG sensor. EEG signals can be very noisy. So the first question is that you think that with this new device, you would end up with signals not so noisy as we had before. And the other thing is that there is always this 10-20 spatial solution of the electrodes. This is a standard way of actually capture the signals from EEG. And we know that there is lots of frequencies of the signals with this electrode. So do you think that we could revisit this spatial distribution of these electrodes with this deep sensor?
That's your question. So, so the first question was about the noise, was that? Yeah. So yes, you're totally right. Usually when you look at those different spectrum of data, all of those different, they're really quite messy. There's a lot going around the brain, and through those stimuli, we need to actually identify a very, very specific type of signal that we can relate back to the stimulus that we need to the person. So it is quite a challenging type of endeavor, and basically that's why we're working together with an AI specialist, because there's two ways that these can be done. One, of course, with the sensor, we want to provide the cleanest and the sensitive type of signal quality as possible. And on the AI side, they need to improve their algorithms as much as possible in order to also on their side to improve person as much as they can. So they work together. And in terms of sensor, I talked a lot about conflict impedance, and of course, conflict impedance is a basic requirement. So ideally, one would have to have something like at least down to 50, so below 200 kilo impedance. And yeah, we're getting close to that. Now, the signal to noise ratio is another part. Distortion as well is another part. The signal to noise ratio starts being a little bit more complex because it's the signal to noise ratio of the actual sensor plus the element system. So basically, in that case, it's very important that the system itself is optimized. So that, and particularly the reference system is optimized. So we really notice very clearly that depending on what type of reference we use, we always have reference in that system, depending on what type of reference. So what type of sensor we use for the reference and where it's the reference and how good the content is there. That's something key as well. Yes. Yeah, dry just because otherwise it would have to be, some applications like gaming and stuff, some of them is still use the wet sensors, but you have to refill after a while. So for some application like this, this is not because it would where the students just really have and need their actual callback numbers. So it's really not easy to stop and refuel all of the sensors during duration. And as that, there's a lot of application where you really like to have it, such that you put it on and off as much as we really want. Now, to respond to your second part of the question, which was the position. The position now is really, as I was quickly explained that before, it really depends really highly on what's the final purpose of the system and what was the paradigm changing in the system. As I said, if we choose, for example, a control-based system like SSVP, it's very important to have multiple sensors in this area here. And what we also realized is that the position of the sensor is person dependent. It's not so SSVP often is used because it's almost no training. So that frequency is picked up directly. There is no embedding of the personal attention or anything, but yet there is still personal dependency on where it is the best location. So in that was part of the demonstration I was able to where we had really high accuracy. We actually used 6 sensors around using the area, and some were not working well. Some were working. So it's a bit of there's still a lot to be improved. Since that's a question.
Any other questions? I have a small one. Are these sensors, they can be used for a long time or are they disposable?
So these ones, in principle, we're aiming to have sensors that are long term. So they can be used, for example, for a whole day, the whole conditions, and very kind of people because some of the pin sensors that I showed before, they actually, after all the users that we had, they basically told us that they made a security that the sensor on the head, they had a headache. Because what happens is that the quality of the content is extremely important. So you really want to push the sensor against the skin as much as possible. And because they have those thick pins, that becomes really painful. So basically, one of their guys were telling them, well, we look forward to having graphene ones because this one's I don't think I can. I can work from longer than I think so.
So if you don't have any other question, I'd like to thank Francesca Iacopi. Obrigada a todos pela presença e boa semana para vocês.